Homework going all right? Yes. For which one? The one I just handed back? I can remember what it is. Oh, so I have a resume for you. Which one was it? Oh, was that the one where I gave you the determinant and then I wrote a matrix down? Is that right? All right. So you have your A is A, B, C, D, E, F, G, H, I. And you were asked to find, you were given that the determinant of A is -7, and you were asked to find the determinant, oh, I could write, find the determinant of A, B, C, G, H, I, D, E, F. Is that right? Okay. Okay. So how is this matrix different from the other one? The transpose, certainly, right? Because normally my letters are written vertically rather than horizontally, right? What do you know about the determinant of a transpose related to the determinant of the original? They're the same, right? So the determinant of this matrix would be the same as the determinant of this one. But that's not quite the original, is it? What's different now? Yeah. Yeah, so we could have swapped the columns to start with, or in this case, I already did the transpose, and now I can swap the rows, right? These rows are in the reverse order. It's 2 and 3. If we swap rows 2 and 3, what does that do to the determinant? Flips the sign. So this would be negative the determinant of, well, the original matrix. So I must get 7 rather than -7. So again, transpose doesn't do anything to the determinant. Then swapping the rows made it negative. So negative of -7 is positive 7. You could have also done a column swap first and then transpose. Column swap has the same effect. The reason why you can do column operations or row operations and have the same effect as the row, you can do column operations rather than row operations and have the same effects is because the determinant of the transpose is the same as the determinant of the original. So you do a column operation on the matrix, it's the same as doing an equivalent row operation on the transpose. So swapping 2 columns makes the determinant negative as well. Other questions? All right, so last time we talked about adjoint. Are we okay with calculating an adjoint? Okay. And then we had the last property at the very end last time that we said if we take the matrix times its adjoint, what matrix do you get? Good, yeah. We get a diagonal, we get a diagonal matrix where every single entry on the main diagonal is the determinant of A. This works for any matrix A, but if A is invertible, we actually get a formula for the inverse of A by rearranging things. If A is invertible, then we can also write the inverse of A as 1 over the determinant times its adjoint. So it gives us an alternative formula, albeit a very, very messy formula. It's very computationally expensive to calculate an inverse this way, but it does give you a formula for the inverse in this fashion. All right. In any event, I want to talk about one more property of determinants that they mentioned in the homework. Make sure that you're able to do the homework problems over those without having to go dig through the book to find it. And then we'll get into talking about some vector stuff today. A little bit of a change of gears, but we're going to come back to doing matrix stuff, and in particular solving systems of equations stuff, as we go through the next chapter on vector spaces. So the applications of determinants that we're going to talk about is determining whether 3 points are on a line or 4 points are on a plane. Okay, so let's do the 3 points on a line piece. So if I just have in my xy plane, if I want to know if x1, y1, x2, y2, and x3, y3 are all in the same plane, they are all in the same plane. If they're all on the same line, we can do a quick check with an area idea. We already introduced determinants as a volume function. Two-dimensional volume is just area, right? I didn't put these on the same line, but if all of them were on the same line, if I think about the triangle or the parallelogram, either way you want to think about it, if they're all on the same line, what would be the area of the triangle determined by those 3 points? It'd be 0, right? So I can make a triangle or a parallelogram, either or, by doing these directed line segments to create vectors. You've probably done this before, right? Have an initial point and a terminal point, right? If this is, I'll label it as V1 and label this as V2, what would be your components for V1? How do you find your components when you have from x1 to x2? From x1, y1 to x2, y2, how do you find your components? Yeah, you subtract them, right? You would have x2 minus x1 for your x coordinate and y2 minus y1 for your y coordinate. You agree with that? Okay. Likewise, for V2, we'd have x3 minus x1, y3 minus y1. Now I have two vectors, and this is exactly how we introduced determinants. We said that the determinant within a plus or a minus could give us the area of the parallelogram determined by those two things, right? And you just told me that if they're going to be collinear, if they're all on the same line, what does the area have to be? It would be 0, right? So we can see that these 3 points, x1, y1, x2, y2, x3, y3, are collinear if and only if our determinant of the matrix x2 minus x1, y2 minus y1, x3 minus x1, y3 minus y1 is equal to 0. Gives us a quick numeric way to check if these 3 points are on there. We do have to remember to do some subtraction. Basically, the subtraction of your x1 for your x coordinates and your y1 for your y coordinates is just doing a translation. It's just moving this point we have in common to the origin. That's all we're doing, right? That's all the subtraction does. So we can check quickly whether or not we have these 3 points are collinear. They do give you a slightly different formula in the book, which doesn't require any subtraction because the determinants they do will do the subtraction for you. You can also do this as the determinant of x1, y1, and a 1, x2, y2, and a 1, and an x3, y3, and a 1 being 0. It will give you the same If you compute the two determinants, you'll get the same answer. If you compute the determinant of this matrix here and compute the determinant of this matrix here, you'll get the same answer. You get the same products that you're getting. Okay. Either one works. It's just a matter of which one you choose. Personally, I like this first one because we already talked about that, right? We said that if we think about the determinant as giving us a volume, then I've got two vectors defined by those 3 points. I'm just trying to figure out what the area is. If the area is 0, then they have to be closed linear to start with. Does that make sense? So you can probably do the same thing for 4 points trying to determine if 4 points in space are coplanar. If you've got, say you've got x1, y1, z1, and x2, y2, z2, and x3, y3, z3, and an x4, I can write, x4, y4, z4. Can you do the exact same thing we just did? Yeah. I can start at one of the points. It doesn't matter which one you start. You're just trying to create the parallelopiped, right? Remember that fancy word, parallelopiped? Okay. Start at one point and make 3 vectors. And then determine if the solid, I know I didn't draw it very well, but determine if the solid determined by those 3 vectors has a volume of 0 or not. Right? And then you can do the exact same idea that we did, right? We're just doing terminal minus initial for our points to get our vectors, and then put it in the determinant. So the 4 points will be coplanar. Oops. If and only if the determinant of the matrix x2 minus x1, y2 minus y1, z2 minus z1. Same thing for x3, y3. Same thing for the next point, and same thing for the other point, for heaven's sake. Again, use one of your points as the initial point, and the other 3 as your terminal point. So you're creating 3 vectors, right? So notice that I've got the minus x1, minus y1, minus z1 is fixed all the way through all 3 rows. The only thing we're changing are the 2, the 3, and the 4 for the other ones. Again, the reason why I prefer this formula, personally, is because of the way I introduced it to you when we started back at the beginning of this chapter, was that we thought of determinant as a volume function, right? So I'm really trying to determine if this solid created by those 4 points really does give me a 0 volume, and so that's not really a solid, they're all on the same plane, or if I really do get an honest to goodness solid that has non-zero volume. But much like what we do over here, and like I said, it mentions it in the book, you can change it to a determinant that looks like this, where it would be a 4 by 4. Your 4th column would have all 1s in it, and then your first 3 columns would be made up of the 4 points that we have. You do it that way as well. It's just a matter of which way you prefer. It doesn't really matter. I just like to introduce it this particular way because it makes sense for what we've already talked about. At least in my mind, it makes sense for what we already talked about. There's a couple of problems on the web assign that ask you to do that, so I want to make sure that we talk about it. But at this point, it's just a matter of plugging it in the formula and see if you get 0 or not. And you can do that on a calculator just as easy as anything else. Does that make sense? And again, like I said, you can create the determinant whichever way you want to do it. Doesn't matter. You can see why it's going to work, I think, because notice that if you expand along the column with the ones, that's not going to add anything to your product, right? So one of the products that you'll get, say for this one, you'll get an x2, y3 minus an x3, y2. And you can see back up in the original, when you multiply, what did I say? You get an x2, y3 here when you multiply those two together, and you get an x3, y2 when you multiply those two together. Right? It's just a matter of keeping track of all those products. That's all it's doing. When you do this one, you get what? An x1, y3. I see x1, y3 here. When you do this one, you get x3, y1. I see x3, y1 here. And you'll end up with the same exact product when you multiply it all out. Just a different way to write it. Again, you can use either. You'll get this. These two matrices have the exact same determinant because of the way the multiplications work. Any questions on that at all? It literally is just a formula to plug things in. At that point, it's just a matter of plugging in the numbers. This okay? All right. Well, let's go ahead and get into the next section or next chapter. The next chapter talks about what we refer to as abstract vector spaces. So we'll start with vectors that we're familiar with, extend those a little bit, and then we'll start thinking of other things as vectors. So what we're going to concentrate on today is looking at vectors that you're used to, R2 and R3, right? We just drew some pictures here. We'll extend that to dimensions above 3 in a natural way and see what properties those vectors have. And then we'll use those properties to define new vector spaces. Okay? So what we're trying to do is come up with a theory that allows us to treat all sorts of different objects as vectors. So for example, we might want to treat polynomials as vectors. We might want to treat continuous functions as vectors. We might want to treat matrices as vectors. Okay? So that's where we're headed. And the reason why we want to do this is because when we prove theorems about certain things, we'd like to prove it for all types of vector spaces, depending on what we're trying to look at, versus just the ones that you're used to with components. Okay. The reason behind that is that later on, or perhaps this semester, if you're, or maybe you already had the class, something like differential equations, one of the things that you worry about when differential equations is writing all the possible solutions to a differential equation. In there you have constant multiples of different types of functions that allow you to write general solutions. All of those, the reason why you can write them that way is you're thinking about those particular functions as vectors and making them combinations. And we'll talk about those combinations in a little later on in this chapter. So this is why we're trying to start with something you're familiar with and abstract it. Okay? And the reason we want to abstract it is because we want to be able to prove theorems, like I mentioned, prove theorems about lots of things at once, as opposed to, I'm going to prove a theorem about this specific thing, and then I'm going to change context and then try to reprove the exact same theorem, even though everything's going to behave exactly the same, and then change context and do it again, and then change context and do it again. That seems like a lot of extra work. So that's why we're going to do what we're going to do. All right. So anyway, section 4.1 talks about vectors in n-dimensional Euclidean space. It's a lot of words. Rn. So we use our boldface R, blackboard boldface R again to represent real numbers. The n just tells you how many components that you have in your vector. So we'll get to that when we get to it. But again, this is referred to as n-dimensional, and it has something to do with the n that's there. N-dimensional Euclidean space. Again, this is what this is going to be is just an extension of things that you already know. So, for example, we know what R2 is. This is just, typically we think of them as ordered pairs, x, y, where each component is a real number. However, as vectors, we need to make sure that we have honest-to-goodness vector things, right? So when we think about R2 as a vector space, this is where we're headed as vector spaces, I need to make sure these are defined as vectors. So when I have a point in the plane, and again, you've already done this if you've had Calc 3, you've already done this if you had physics, okay? But we're just we're concentrating on making this stuff exact because, again, I want to abstract it later, okay? So some of the stuff that we're going to be talking about today probably seems very obvious, which is good. It should seem obvious, but again, we're looking at the property, not the object, okay? That's the idea. So again, to get a vector, I'll make sure that I have something where all of them start at the same place, right? So we started with the origin and think of this as my object. So it's important to know by context if you're talking about a point or if you're talking about a vector. Even though we're going to use the same notation, we're going to use what looks like ordered pair notation. When I write it this way for a vector space, I really am not just referring to the point, but I'm referring to this object, this vector. Geometrically, we think about it as starting from the origin and going out to the point. R3 is defined similarly. We would just have ordered triples. So hopefully you can see how we can extend this pretty easily by definition, okay? Even though it's a little bit more difficult to see visually what these vectors might be, when we're talking about Rn, we're looking at, n tuples, where each component of your n tuple is a real number. So that's all we mean by vectors in Rn. Again, this looks like I'm referring to a point, but if we're talking about vector spaces, this really is just has some sort of an object. If we think about the origin being a thing with all zeros in it, then we're thinking about the object that goes from the point with all zeros out to that point geometrically. I mean, visualizing things above 3 dimensions is, well, for me, it's impossible. Okay. All right. That's all we mean by vectors in Rn. So what we're going to be interested in is how do we do operations with vectors in Rn? And then what properties do those operations have? We're going to talk about two main operations, and we've already talked about them before when we did our discussion with determinants. You talked about them before in other classes, most likely. Those two operations are combining two vectors together with addition and multiplying a vector by a scalar. There are other products that you might do with vectors. If you've had Calc 3 or physics, you've probably talked about a dot product or a cross product. Okay. Those are special operations dependent upon special instances of vector spaces. The operations that we need for abstract vector spaces are the two that I mentioned, being able to add two vectors together and multiply by a scalar. Okay. For vectors in Rn, you already know how to do that. We just talked about it a little bit ago, and we've talked about it before. When you add two vectors in R2, if I wanted to take the vector 1, 3 and add the vector 5, -1, what do you do? Yeah, you just add the corresponding components, right? Add the 1 and the 5 together to get 6. Add the 3 and the -1 together to get 2. Was there anything special about doing that with 2 coordinates? Because you do the same thing with 3? Yeah. So you think you could do the same thing with n? Yeah. So we define addition of vectors in Rn in the same way. If I have x1, x2 out to xn, and want to add y1, y2 out to yn, I just do this component-wise. And add the components together. There was nothing, basically what we're saying here is there's nothing particularly special about doing two ordered pairs or ordered triples. We can just do it for as many components as we want. Likewise, if you wanted to do 7 times the vector -3, 4, -2, and do that scalar multiplication, what would you do? Yeah, multiply all the components by that 7, right? Do you think it's going to be any different for if I make a vector longer than 3 components? No. Okay. So we're going to define scalar multiplication in Rn as if I have a scalar C and a vector x1 out to xn, we'll just take that C and run it through everything. Like I said, nothing different than what you've talked about before. We're just extending how many components out you go. By the way, we will stop at a finite number of components for a vector. It is possible to have an infinite number of components for a vector, but then things can get a little strange as objects, and you have to, depending on what the space looks like, and you have to do a couple of different definitions depending on what your space looks like. So everything that we will do, we refer to as finite dimensional vector spaces, but do know that there are infinite dimensional vector spaces. We'll actually mention a few of them, but anytime we talk about those particular vector spaces, we'll usually want to just drill down to a piece of them anyway. I'll talk about what I mean by that later. Okay. As far as components go, though, it is possible to define things where these go out to infinity. You have an infinite number of components. And you can still define the operations the same way. Just sometimes they get a little bit weird. Anyway. All right. Bless you. The reason why we talk about these first is because these particular things are familiar to you, right? You know how to do these types of operations. We want to abstract on these things. So one of the things that we want to abstract is what properties do addition and scalar multiplication have that we actually might be interested in looking at. So let's talk a little bit about, say you wanted to go back and solve a small equation. So this is gives you an idea of some operations that we might want to be able to do. Okay, so thinking back to, say, algebra class back in, well, maybe even junior high, if I wanted to solve the equation 3 plus x equals 9. I know, not hard, right? But let's think about what we would try to do from a standpoint. I've mentioned this a little bit before, but think about what you might want to try to do to solve this equation, what operations you actually have to do, right? What would you need to do to solve this equation? Okay, so subtract 3. Subtraction is defined as what? It's the adding the opposite, right? Adding the inverse of it. So the first thing I need to know for a fact is I need to know what the negative of 3 is. I need to make sure that it has an inverse, right? In order to do that. So to be able to subtract 3 from both sides or add a -3, to be able to do this, we need to know that -3 exists. I know it sounds weird, but I need to make sure that we actually have an object that I can add to 3 and make it go away, right? That's something we would need. Okay. All right? Okay. Notice I wrote this specifically with parentheses on the left-hand side as well. Notice that if I'm assuming that my plus is defined here by writing this to start with, right? I'm assuming that I know what addition means. So that's another thing we actually need to know before we even start this whole problem is I know what this symbol means. That sounds weird though, right? Okay, but I need to know what this symbol means before I can even start. Okay, all right. Notice though, if I know what the symbol means, is 3 plus x, whatever that happens to be, represents a single object. So whatever that object is, I'm adding the -3 to it. So my parentheses are here. The whole reason why you told me to add -3 or subtract 3 is to make this 3 go away. So what other property better we have in order to make, put this -3 with that 3? What other property do we need? Associativity, right? I need to be able to regroup, right? So in order to be able to do -3 plus 3 this way, I'll just write that as 6 since I know what that object is. We need associativity of addition. That's another thing that we need to have happen, right? We agree? Okay. Now, the reason why we use -3 rather than, say, 7 is because that makes this equal to what here? 0, right? Well, then I need to know that there actually exists a 0. I know, weird stuff, right? Okay. And then finally, this last part is also the fact that you have a 0. The fact that we have a 0 means that if I add 0 plus x, we just get x, right? Okay. So notice that there are 4 things in here. I didn't write one of them down, but there are 4 things in here that you absolutely positively have to know exist in order to be able to solve this problem. Even though you told me right away that the answer was 6, right? I need to make sure my addition makes sense. I need to know what this symbol means. I need to have inverses. I need to have regrouping. And I need to know what 0 means. All right, there's 4 different things in there. All right. We also would like the same answer if I had x plus 3 equals 9, right? Make sure we get the same number either way. That's commutativity. So if I want to make sure that the answer also works the other way around, I need to make sure my addition is commutative. Right? Okay. So there's 5 properties that we need right off the bat, and none of them even involve scalar multiplication, did it? Let's think about another idea. What if you wanted to solve, I'm not going to go through it all painstakingly like I just did a second ago, but what if you wanted to solve, I'm going to write it weird, 4x plus 3x equals 7. What was you, just thinking about what you would do algebraic, I know you know the answer is 1. Okay. Algebraically, though, what do you do first on the left-hand side? Yeah, I need to kind of combine the like terms, right? I also need to make sure my scalar multiplication is defined, right? I need to know what 4 times x means, don't I? I know it's weird, right? But I also need to make sure that I can combine like terms. Well, combining like terms really is just factoring out this common factor. You've done that several times solving for things that have multiple variables in them, perhaps, right? Factor out a common factor so that you see the 2 pieces together. One instance that I can think of pretty notable is when you're doing implicit differentiation in Calc 1, you collect your dy dx's on one side so you can factor it out, right? I need to be able to, that property actually makes sense, right? I need to make sure I have a distributive property, right? I need to make sure that I can distribute a scalar multiplication over a sum of scalars. Okay. make sure that idea makes sense. So in order to combine this into 7x, really this is what you're doing, right? Right? So this is a distributive property. There's actually two of them for scalar multiplication. Okay. It's a distributive property for scalar multiplication. I'll combine these to 7x equals 7. Now remember, the 7 is just a real number, so the fact that I have 1/7 is not an issue. However, if I multiply both sides by 1/7, I still have an associativity issue, don't I? Oops. I actually want to multiply both sides by 1/7. All right, I still have an associativity issue. So to be able to get this to be a 1 on the right-hand side, I need to regroup. So I also need to worry about some sort of an associativity property. Why did I use 1/7? Well, 1/7 times 7 is 1, all right? And then I also need what we typically refer to as a unitary property or preservation of scale. I need to know that 1 times a vector really just does give me the vector back again. All right. I didn't illustrate the other distributive property, but there's actually two distributive properties. This is scalar multiplication distributing over a scalar sum. 4 plus 3 is just the addition of two real numbers. But I could have also had a scalar and two vectors that I would need to distribute over, perhaps as well. So again, there's not this particular example, but there's 5 scalar multiplication properties as well that we need to worry about. It turns out that your real numbers, your Rn, all your vectors in Rn, satisfy these properties by the way we define addition and scalar multiplication. Okay. So I just want to make sure I get the numbers in order. I'll open up our book because I want to make sure I match the numbers in the book to the different properties that we have. So this is theorem 4.2. They're going to let U, V, and W be vectors in Rn, and C and D be scalars, so they'll be real numbers. All right, so we're going to have 10 properties here. We should be able to prove all 10 for this particular vector space. We're not going to, but we should be able to prove all 10. They're good ones to practice on. The first one basically says that addition is well defined. We usually refer to this as closure under addition. By the way, these properties that we're gathering here for vectors in Rn, these are going to turn into our vector space axioms. So when we start treating things as abstract vectors rather than worrying about vectors in Rn. Okay. This just says that I have a way that I can actually combine two vectors under addition. Now, it may be the case that addition isn't normal addition. We may define it weirdly, but that's all this says. We have closure under addition. Okay. The second one says that we can add in either order. Yeah, that's right. So we have U plus V is equal to V plus U. That's a U, not a W. I don't know why I'm insistent on writing a W there. I can add in either order. That's fine. It's a nice property that we want for vector spaces, vectors in general. The next one is associativity. This is the number order I would have expected these to pop up in this theorem, but I just wanted to make sure. Before I start writing down more of these, I want to talk about how you would end up needing to verify these when you come across a vector space problem, checking something is a vector space. In these, you really are doing straightforward checking. If I add two things together, do I end up with an object back where I started? That's what closure means. To give you an example of something that's not closed under the operation, if I take positive integers and make my operation subtraction, is that closed? If I subtract any two positive integers, do I end up with another positive integer? No. Okay? For the first one smaller than the second one, I get the negative number, right? Subtraction is also not associative, but or commutative for that matter, but it's not closed, right? For that particular one. Okay? So that's what we mean by closed. You start with two things in your set, you do the operation, it lands back in the set. Okay? Same thing with the integers. If I multiply two integers, do I get another integer? Yes, so that would be closed under multiplication. But if I divide two integers, do I necessarily get another integer? No, so that's not closed under division. Again, closure is just a matter of checking. If you combine two things together with the operation, you end up with an object like what you started with. So it makes sense when you're doing this with Rn, right? Because all you're doing is just taking real numbers and adding them component-wise. If we add real numbers together, we get a real number. So we're good. So it is closed. Same way with why commutativity works and associativity works, because where are your operations in Rn really taking place? They're just taking place in each component. In each component, it's just real number addition. Real number addition is commutative and associative. All right. So the first three really are just checking things. The next two, you have to actually go out and find something. The fourth one says that there exists a vector that will call 0. In this case, it's in Rn, so that u plus 0 equals u equals, well, I'll write it the other way around. I don't need to since addition is commutative. But I have a 0 vector. When I add the 0 vector to the view, I get u back again. So this is existence of a 0 vector. Why am I having issues spelling today? Now, just because we said something is the 0 vector, it does not mean that it is necessarily the number 0. Okay? The 0 vector depends on the operation. Okay? In fact, the operation here, it's not the number 0, it's going to be the vector that has all zeros in it, right? Okay? But it depends on what the operation is. If you were saying, hey, by the way, I'm really going to make addition and multiplication. I'm going to define addition as multiplication. I can, because I'm just saying it's an operation, right? What would your 0 be then? If you changed it from addition to multiplication, what would your 0 vector be then? So remember, it has to be, you have to, when you do the operation, you have to get back what you started with. What does that with multiplication? 1, right? So in that case, your 0 vector would be 1. We still call it a 0 vector for vector spaces, but in that case, that 0 vector would actually be the number 1 in that case if we're doing this multiplication. I know it's weird. But again, the zero vector, you have to go find it, and it's relative to your original operation, however it's defined. All right. Once we have a zero vector, we can do inverses. Let's write it this way. There exists a negative u in Rn so that u plus negative of u is the zero vector. And of course, since it's commutative, it works the other way around. Again, in Rn, it's not hard to identify what these things are. It'll be more challenging to identify what they are in other vector spaces, depending on what the operation is. Notice that if you don't have a zero vector, you can't have inverses, right? Without 4, you can't have 5. You can't get back to the zero vector if you don't have a zero vector, right? But just because I have a zero vector doesn't mean I'm going to have inverses. To give you an example, do the positive integers again under addition. Or I'll say the non-negative integers under addition. So I'll include 0 in there. The non-negative integers under addition satisfy the first 4 properties, right? But not the 5th, because I don't have any negatives. I can't get back to 0. If I don't know, that type of algebraic object has a special name, but I'm not going to talk about it today. But anyway, just because I have to have 4 in order to have 5, but just because I have a zero vector does not mean I have inverses for everything. That's the important part. Okay? Try to emphasize that point. All right, so these are the 5 axioms for vector spaces that have to do with addition. There's also 5 that have to do with scalar multiplication. This is just saying that my scalar multiplication is well defined. Remember that we're going to be working with what are referred to as real vector spaces, meaning that our scalars are real numbers. There are also complex vector spaces, in which case your numbers will be complex numbers, or your scalars would be. Okay. So to give you something that wouldn't be closed under scalar multiplication, say you started with rational, you do all your vectors like Rn, except that you only use rational components or integer components. Then I wouldn't have my scalar multiplication, wouldn't be well defined because I couldn't do something like square root of 2 times a vector. Okay. Anything that has to do with scalar multiplication, assume the scalar is a real number. Okay. Because we're going to deal with real vector spaces. All right. So again, if you start with something that says all my vectors have to have integer components, then that would not be closed under scalar multiplication. Because I could multiply by an irrational number, and I would get something that's not in my space. All right, the other ones have to do with the properties we mentioned. I'll write them down relatively quickly here since we're almost out of time. The next two are distributivity axioms. I will mention something about the 8th one here real quick before I write down the last two. What are we adding together on the left-hand side? Two scalars. This is, no matter what the problem is ever, this is regular old real number addition. Okay? What are we adding over here? two vectors, that might be a different addition. Okay? But the left-hand side of this one, this is always scalar addition. This is always regular old, I'm adding two real numbers together. Okay? And I want to make sure I mention that. So both of these are distributive properties. Finally, I'm out of time, I'm sure. This one is your associativity property. Again, like your addition one, this one here, this is regular old real number multiplication. This is your scalar multiplication in two spots. Okay? This is right, associativity there. And the last part is the 1 times a vector is just its vector. All right. We'll do some more examples of this next time. We'll actually use some honest to goodness numbers, but I wanted to emphasize what we're doing here because we're going to abstract these notions. Okay? These will be your vector space axioms. All vector spaces have to satisfy these things. Okay? But things might get weird depending on what your vectors look like. All right? So let's start doing that next time. Homework due Friday that I gave you. Your web